Hello, and welcome to my poster presentation. First off, thank you for your interest in our work. I'm Alejandra Mendez, and today I'll show you some of the central ideas of a recent work we've published together with Claudia Montanari and Jorge Miraglia. We work at the Instituto de Astronomía y Física del Espacio from Argentina. In the next couple of minutes, I'll briefly describe some of the scaling rules we studied for the ionization of biomolecules by the impact of bare ions. This contribution constitutes a follow-up on a recent work where we proposed a straightforward model to determine the single ionization of complex molecular compounds. By implementing this approach, we computed the total cross-section of a 108 collisional system composed of 6 different projectiles: antiprotons, protons, and bare ions of helium, beryllium, carbon, and oxygen. All of them impinging into various molecular targets, including DNA nucleobases, hydrocarbons, and small molecules such as water. The ionization model we developed considers the independent atom approach. Following the stoichiometric formula of the molecule and non-perturbative CDW with equal initial state calculations, we can straightforwardly determine the single ionization cross-section. Although we only considered a few molecular targets, thanks to our model, we can obtain the cross-section of any molecule composed of hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur. The first scaling rule we consider is the mother of all scaling rule, the Taburin rule, which consists on scaling the ionization cross-section with the number of its active electrons. The Taburin rule considers a certain set of weakly bound electrons. This figure shows the implementation of this set of numbers to our theoretical calculations. However, by inspecting our CDW calculations, we propose a new set of numbers, which we call CDW numbers, which allow us to reduce the width of the band where our theoretical results lie. Each of these bands correspond to a particular projectile, and each of the curves in those bands to a molecular system. We also implemented the modified scaling rule to the available experimental data and got a pretty good outcome. Furthermore, we inspected the scaling with the incident projectile and its charge. In our first work, we used the widely known zeta square scaling that follows the ionization cross-section at high impact energies. However, we studied other scaling rules with the ion charge and finally considered the scale proposed by Montenegro and collaborators. This scaling rule introduces a factor alpha into the sigma over zeta squared and maintains that relation by also scaling the incident energy. Now, by optimizing this parameter to our theoretical curves, we were able to locate all of our results into a single narrow band. Now we have the opposite effect that from the previous scaling. Each band now corresponds to a particular target. For example, here we have uracil and water, and each of the curves laying in the band correspond to a different projectile. Finally, we combine the two previous scales into a single universal scaling. This particular scaling is general and independent of the collisional system. We tested this universal scale with a significant amount of experimental proof data and got a reliability of about 35%, which for a first-order approximation is not that bad. To summarize, in this contribution, we proposed and modified 3 scaling rules to determine the ionization cross-section of any molecular compounds composed of hydrogen, carbon, nitrogen, and oxygen by the impact of bare ions. If you have any questions or comments, please join me at the second poster session next 28th of July from 4 to 5 p.m. US Central Time. See ya!